Okay, this video will mix some of the old with the new, I guess. We'll look at reviewing some of the concepts we covered earlier in this chapter, and of course we'll look at a few new inquiries here as well in part C and D. So we'll focus on part A for now. We'll shut these other ones off for a few more minutes. So part A is asking us for the average rate of change of this function over a specific interval, where x belongs to the interval of 1, including 1, all the way up until 3. And if you're not familiar with interval notation, all that means is we're only looking at x values, where x is greater than or equal to 1 and less than or equal to 3, using inequalities instead of that interval notation. You should familiarize yourself with interval notation because it's used in a lot in calculus. So that brings us to, I guess it's really just a new term, what the average rate of change is for a function, and that's just a secant slope. That's all we're looking for here. So this is definitely earlier parts of the stages of this chapter of the derivative, where we started off by looking at a secant slope. So we're going to actually label it that way. So the average rate of change, if you're asked for that, you're just being asked to do a traditional slope calculation. And some of these can get a little bit tedious. This one's not too bad because remember we need to figure out our two y values. So this will be our first x value and our second x value. So of course to get our two ordered pairs we have to input x equals 1 and x equals 3 into our function. So I think we'll just use function notation. So this is the difference in our two y values, and that'll be over of course the difference in the two x values. So why am I writing subscripts there? I guess we'll just use the numbers, 3 minus 1. So right now it's f3 minus f1 over 2, so we have to take, I guess, a few seconds here to calculate the y value when x equals 3, and also the y value when x equals 1. Some scrap work over here. So 3 cubed, once we input 3 into this function, will give us 3 cubed, or 27, minus 4 times 3. So that's 27 minus 12, which is 15. So there's our y value when x equals 3. And our second y value, well, I guess actually our first y value, if we use the subscripts, that will be 1 cubed, or 1, minus 4 times 1. So 1 minus 4 is negative 3. So we can go back. We can calculate the average rate of change now for this function over this interval, where x is going from 1 up to 3. So f of 3 is 15. F of 1 is negative 3. So watch your two negatives there. And I think at this point we can say 3 minus 1 is 2. So we get 18 over 2. So our average rate of change is 9. So just to be clear, that's your average rate of change for this function. No tangent slope, simply a secant slope. Okay, part B, I guess in contrast to part A, which was looking for a secant slope, part B, you can probably guess, is looking at a specific location. It's looking for an instantaneous rate of change. So that, of course, is a tangent slope. And I guess if you want to use first principles, go for it. But of course, that's probably a terrible idea at this point. Since we're liberated from first principles, let's use our power rule. And I guess our basic differentiation rules and properties here as well. So we're going to differentiate. I think I'll just use one color here. We're going to differentiate both pieces involved in this difference, since this is a difference of two functions. I better slow down the penmanship here. So that's a cube. And then minus the derivative of 4x. Okay, so remember we can bypass that coefficient. And I guess we'll hold off on our differentiation for one more step. And like I said in the previous video, if you can skip some of these steps and you really just think what I'm writing down instead of actually taking the time to write it down, if that works for you, that's more efficient and it's probably a little bit better approach. Anyway, so let's differentiate the first term in this difference of two functions. So the derivative of x cubed is 3x squared. And then we're going to bypass the 4 coefficient. And we're going to take the derivative of x, which of course is simply the coefficient of x, since that's a linear term. And I guess we'll end up with 3x squared for our derivative, minus 4. We'll label that as f prime of x. Now we're not done, because of course we're being asked to figure out the instantaneous rate of change when x is equal to 1. So let's get a little more space. So when x is equal to 1, we just pop that into our derivative. f prime of 1, it's going to be 3 times 1 squared minus 4. So of course that's going to be 3 minus 4, or negative 1. So we have our tangent slope at a specific location, which remember we're now calling that instantaneous. We're calling it an instantaneous rate of change. I don't care, I guess, what terminology you use. It's just basically be able to recognize tangent slope, slope of the curve, instantaneous rate of change, all being one and the same, just depending on the instructions, I guess, that's obviously given in the problem. Okay, so part C, which is directly related to part B, we're getting some, I guess, a hence moment here, some flow. We're looking for the equation of the tangent line at x equals 1. And remember, a few minutes ago, I erased it to get some space to work, but we found our derivative. I guess we don't need to write the entire derivative again. When we input 1 into our derivative, we had a slope of negative 1. So in this question, we're working with slope. We know our slope, and that's actually a tangent slope. We're looking for the equation of the tangent line. So of course, it makes sense that we're using the tangent slope, so that instantaneous rate of change. And if we can figure out our point of tangency, this of course is 1, and f of 1, we have a point, which maybe I'll use subscripts x1 and y1. We have our slope, so it should make a lot of sense that we're using our so-called slope-intercept form. So if you remember that, it's y minus y1 equals slope multiplied by x minus x1. And remember, all that is a rearranged slope formula where we drop the second subscript because, of course, we need to maintain an x and a y in our equation. So I guess we can remind ourselves, and I guess I'm reminding myself, what was this y value when we input 1? So of course, if we take a quick look at that again, f of 1 is going to be 1 minus 4. So of course, that's negative 3. So I think I'll just erase this f of 1 and replace it with minus 3. And I might as well get rid of this scrap work there as well. Okay, so we have our point, and we got our slope, and it happens to be the tangent slope. So in this case, our equation will be a tangent equation. And then this is actually takes us back to an earlier chapter. So let's go ahead and set up our point slope form equation. Now, of course, this is the equation that the TI and SPIRE will give you as well. So once we eventually get through these this 4-part question, I think we'll do a quick wrap-up of everything we found here and looking at how you can check your answers on your TI and SPIRE. So y minus y1, so y subtract that negative 3 equals your tangent slope, which I'll write the negative 1 so you can be clear what I put in there. And then it's going to be multiplied by x minus your x value. So this is going to be y plus 3 equals, let's expand this out, minus x plus 1. And then finally, our equation of our tangent line is going to be minus x plus 1 minus 3, which is negative 2. So there's the equation of our tangent line. At this one specific point of tangency. Now, I guess the connection to part B was really that we could use the same tangent slope that we already calculated, so watch for that. It's possible, I guess, in some questions they might make you change your point of tangency to come up with a separate tangent line. Okay, finally, part D, we have to determine another x value where the slope of this function is the same as the result in C. And I think I actually meant to type in result in B. But as long as we know we're looking for an x value that has the slope of either the same as the slope we found in part B, which of course was the one we reused in part C. So I guess it really doesn't matter that I think there's a small typo there. So essentially we're trying to figure out where we can get our tangent slope, hence our derivative, to be equal to the same tangent slope that we found in part B and also used in part C. So remember that tangent slope, of course, was negative 1. Now, since I don't have it on the screen here, I better rewrite our our derivative that we found way back in part B. So the derivative again, which won't take too long to rewrite, just differentiate this function. So this will be 3x squared, and then in my head I'm just going to differentiate both of those pieces again. differentiating x cubed, and then minus 4x. So there's our derivative. So we need to figure out how we can make this derivative equal to -1. Now let's use some common sense here as well. We hope that our answer returns x equals 1 again, because remember that was the x value, the point of tangency, that was both of these previous questions as well. So that's a good way, I guess, to check your work once we set up our work here. So let's actually go ahead and do it. So instead of using f prime of x, we can use the actual expression for our derivative. Now it's a quadratic expression, which is why we can get up to 2 answers here. So when can I make this quadratic, or get this quadratic to be, output the number -1? Or where can I get this quadratic to be equal to -1? And that's not terribly complex. We'll just add 4 to both sides. So we'll get 3x squared equals 3. We'll divide both sides by 3 to get 1. And then we'll definitely use our plus or minus roots here in this case. So the square root principle, just to make sure you're clear where the 2 possible answers come from. And we get our x equals 1, and we get our x equals -1, which is our other new x value. So determine another x value where the slope of this function is the same as the result in, I guess, parts B and C. Of course, that is going to be x equals -1. And it's not asking for coordinates or anything here, so we can just list the x value. Okay, let's quickly, I guess, but not too quickly, take a few minutes to go through, see how we can double check our work on the TI Inspire for all these questions that we just completed analytically on pencil, using pencil and paper. Okay, so here we are in our TI Inspire. Of course, we'll open up a graph and we'll punch in our cubic polynomial that we just worked with fairly extensively. X cubed minus 4x. You can see what that thing looks like. Here it is. And yes, we'll start moving some labels around. And the first thing we did, part A, remember, was an average rate of change. So this visual hopefully will allow you to understand what an average rate of change is. So I'm just going to use my trace here, graph trace. And I remember my interval was what, 1 to 3. So we'll put both ordered pairs on here when x equals 1. And when x equals 3, and you can see that that actually goes off the way up here because that's an a y value of 15. So if you can master this, there's a nice, well, I guess I'm going to have to escape here first to get the little hand grabber tool to show up again. You can scale your axes down. The only problem I find with that is it scales both axes, and then I can't see anything on my x-axis, but that would suffice if you're working with your handheld device there. As long as you can see the 2 points, I think you should be good. Now if you can master this and master, I guess, a right click, which is control menu, right, then you can click and hold that x-axis, and if you can hit your shift button, remember, which is right here, that shift button labeled shift, you can actually just move one axis as well. Now I have to make sure I click my mouse pad here as well. So that's a very slick feature. That does take some practice though. Anyway, let's get back to what we should, I guess, be focused on. Let's draw a line between those 2 points. And of course, that's under geometry, number 1. And there's no secant line there. I guess you could use a segment, but a line will just keep going once we go through those 2 points. And that is that. And we'll hit escape. And unfortunately, we don't know what the equation or the slope of that line is. And you got 2 options here. If you can hover on that line and master that right click, you can actually turn on coordinates and equations. And look at that. If somebody even did ask you for the equation of that secant line, you would have that as well. But of course, the coefficient on that x is the slope of that secant line. So we'll get into I guess the deeper meaning of average rate of change a little bit later once we get a little more calculus under our belts first. So for now, just understand average rate of change just simply means secant slope. If you're having problems right clicking, then let's just go back, use the more, I guess, basic feature where if you go under geometry and measurement, remember the slope measurement tool that's there, you can click on that line and it'll just give you the slope of that line. That should work as well. So there's part A, our average rate of change, that secant line. Of course, we just wanted the slope between those pair points, 1 and -3 and 3 and 15. Okay, and the next one was we wanted an instantaneous rate of change at x equals 1, and then we wanted the equation of the tangent, so we can definitely handle both of those if we just plop a tangent line on one of those 2 points that we have there, the correct point of tangency. So if I click on this one, you can see our equation of our tangent. So if I hit escape and drag that label so I can see it, it confirms what we found analytically, that the equation of that tangent is -1 minus 2, and of course it also shows us that the slope of that tangent is -1 as well, the coefficient on your x value. And the last thing, we'll put one more ordered pair on our graph using the trace feature, which is what I find easiest at least. So we'll go -1, hit enter, and hit enter again. And there's our third ordered pair on this function. So escape, and yep, move a label, which is kind of, this comes to be, I guess, be expected when you're working with the Inspire. It loves its labels, but they are useful. And then we'll just do our geometry, points and lines, tangent feature one last time. And we didn't need to come up with the equation of this tangent line. We just, all this is doing is confirming that those tangent lines are parallel and they both have the same slope. And remember, all we cared about was the x value of that last point of tangency there, which of course was -1. Okay, so there it is. There was a fairly, I guess, extensive, elaborate 4-part question that offered an excellent review of everything we've covered so far in this chapter. And if you're able to get through all of that, I think you're in pretty good shape for our chapter on the derivative. And also, if you can manage these TI Inspire features that we've been using over and over again in the last number of videos, that should bode well for you when we get into some paper 2 situations in the future as well.